Hello and welcome to WinXAS Tutorials, where I want to revisit EXAFS analysis of copper samples. This is somewhat of a follow-up to the previous tutorials about using experimental and theoretical phases and amplitudes for EXAFS refinement. As always, the WinXAS software and the XAS data I will be using in the hands-on session can be obtained from the WinXAS website. In the previous tutorials, we used theoretical and experimental phases and amplitudes for an EXAFS refinement to the first shell of the Fourier transform chi of k of copper metal. On the one hand, the copper foil spectrum was used to extract experimental phases and amplitudes, which were then used in an analysis of the EXAFS function of copper clusters. On the other hand, the amplitude reduction factor was obtained from the copper foil spectrum and used in the subsequent refinement of copper clusters. Both approaches agreed very well and yielded a decreasing coordination number and distance and an increasing disorder. EXAFS refinements to higher shells in the Fourier transform chi of k clearly required including both single scattering and multiple scattering paths to obtain a good agreement between theoretical and experimental EXAFS function. The large number of paths required carefully correlating certain parameters to reduce the number of free parameters in the refinement. Therefore, we already used several of the available options, and more will be used and explained in this tutorial. At the end of the previous tutorial, we performed the EXAFS analysis of the copper foil spectrum, obtaining a set of Debye-Waller factors to be transferred to the analysis of the spectrum of copper clusters. Here, the Debye-Waller factors were fixed and the coordination numbers were refined. In both cases, we observed a good agreement between experimental and theoretical EXAFS functions. However, coordination number of the first shell resulting from this approach were smaller than that of the single shell analysis. This is not surprising, given that we know from the first shell analysis that while the coordination number decreases, the disorder increases. Hence, the resulting coordination number should be larger. Apparently, this is not the ideal approach, and we may want to look for alternatives. Experimenting with possible alternatives is the subject of the hands-on session which comes next. Objectives will be EXAFS analysis of copper spectra using theoretical phases and amplitudes for higher shells in the radial distribution function. Distances, coordination numbers, and disorder parameters are to be refined for both foil and cluster spectra, and the parameters validated by the single first shell results. The copper spectra and theoretical phases and amplitudes used are included in the tutorials data folder, which can be obtained from the WinXAS website. Let's get started with the copper foil spectrum, Fourier transformation into the R space. So we are going to perform EXAFS simulation and EXAFS refinement in the R space to the pseudo-radial distribution function. So because we do want to refine coordination numbers, distances, and Debye-Waller factors at the same time, it's a good idea to start simple, which in this case means to only use the single scattering shells if possible. And so the first thing you want to do is simulate a theoretical EXAFS spectrum by only using the single scattering shells in this range. And we can set the zero shift to about 4, which we know from the first shell analysis, and we can just calculate Debye-Waller factors using the correlated Debye model and then we can compare experiment and simulation. And we see that we get a reasonable agreement in phase and amplitude, except for this part here where we are clearly missing multiple scattering shells, those so-called focusing or lens multiple scattering shells that contribute significantly in this range. So we cannot hope to get a good agreement between experiment and theory by just using the single scattering path. We do have to include the multiple scattering path in the simulation and also in the EXAFS refinement. So let's include the multiple scattering path in the simulation, reset the simulation, and now we are going to include the multiple scattering path. Here again would be a good idea to start with the most significant multiple scattering path based on their contribution, and then, if need be, increase the number of multiple scattering paths that are included in the simulation and refinement. I'm going to skip this part and just jump ahead and use all the available multiple scattering paths in this range, transfer, and okay. So again, we use the known value for the E0 shift, and so now we can calculate the Debye-Waller factors using the correlated Debye model. This time I'm going to use the potential button here so that we have the Debye temperature here as a parameter that can be varied then in the simulation. So click on OK. And already we see a significant improvement in the agreement in the imaginary part, so in the distances basically. But we see disagreement in the amplitude, a good match in the first shell, but then an increasingly poor match at the higher shells. So this is nothing that we can change or improve by changing the Debye temperature, just briefly checking. Here's the Debye temperature. So if we decrease the Debye temperature, then we get a decrease in amplitude, a better match at the higher shells, but of course a poor match at the first shell. And if we increase it again, we are back at this poor match. So this basically means that the Debye model is basically underestimating the disorder at higher shells and is not significantly or not sufficiently dampening the contribution of the multiple and single scattering shells to the higher distances. So we're probably in the refinement, since we do want to refine coordination numbers and the Debye-Waller factors at the same time. We can probably, in the simulation and in the refinement, not use the correlated Debye model. So what are the available alternatives? Looking at the parameters, we are calculating the single scattering shell Debye-Waller factors using the correlated Debye model, while the Debye-Waller factors of the multiple scattering path are calculated from an average. So there are different options now how to calculate the average, how to calculate the Debye-Waller factors of the multiple scattering path based on the constituent single scattering path. And we can change that here, down here, and we can try a different option here for this average, for the calculation of the average. And you can just click on exit, and we see this reduces the contribution of the multiple scattering shells, but those are basically most important in this region here, and using this different option of or to calculate the Debye-Waller factors of the multiple scattering shells now here results in a poor match at
in particular this distance here between experiment and theory. So probably this is not a good idea. And there is another option here that we can try and calculate. But this, on the other hand, now this results in an increased amplitude, basically, of the multiple scattering path compared to the single scattering path, and also does not improve the agreement between experiment and theory in this range. So this does not seem to help. So basically, I just wanted to show the available options. So going back to the regular calculation, and let's see what else is available now to obtain a better agreement in amplitude. In particular, the agreement in the imaginary part is already quite good, definitely sufficient for starting the refinement, but the agreement in the amplitude is still poor, and we want to improve that. So in the next step, we want to adjust the Barbour factors of the single scattering shells by hand and see if a good agreement between experiment and theory, in particular at higher distances and between the amplitude, can be achieved. So we are going back to simulation. We want to reset the flags, basically, so the correlations, but we want to keep the value. So just click on OK. And now we are using this average option. So basically the Barbour factors of the individual single scattering path are free now, and only the Barbour factors of the multiple scattering path are calculated based on this average. And this allows us now to change the Barbour factors of the individual single scattering shells. So we already have a good agreement in the first shell. There's no need to change anything. But here we can increase the Barbour factor, which decreases the amplitude and results in a better agreement here. And then we continue. You see there is an MS, which means those are the multiple scattering path that we do not want to change. We are looking for the single scattering path here, and we want to increase the Barbour factor and by that decrease the amplitude and see if we can, by hand, get a better agreement between experiment and theory. So here's the next single scattering path, and then this is the last one. So we increase this, and yeah, we can get a pretty good agreement between experiment and theory here. So the calculation of the multiple scattering paths, the Barbour factors, is not the problem. It is really a question of how to calculate the Barbour factors of the higher single scattering path in the refinement. We could just set them free and vary them independently in the refinement, and this is of course the first thing we are going to try. But as we will see, this is not a promising approach, and we will need to look for alternatives. So let's try an EXAFS refinement. We use the same number of single and multiple scattering paths. We select a suitable range in the pseudo-radial distribution function, and okay. So now question is, what can we use to reduce the number of parameters in the refinement. We have a total number of 29 independent parameters calculated based on the Nyquist theorem, and currently we have a total of 65 free running parameters in the refinement. So we significantly need to reduce this number. Well, first of all, we can of course fix the amplitude reduction factor. And now we have coordination number, distance, and the Debye-Waller factors. We do want to refine all of those in one way or another because we know from the first shell analysis that going from the foil to the clusters, all those parameters basically change. So what are the available options? Well, first of all, for the coordination numbers, we can use the multiple scattering button here, basically calculate the coordination numbers of the multiple scattering path based on the coordination numbers of the constituent single scattering path. We can do the same for the Debye-Waller factors. This is basically what we just did by using the average button here, which calculates the Debye-Waller factors for the multiple scattering path based on the constituent single scattering path, and the Debye-Waller factors of the single scattering path are varied in the refinement. So in theory, we could do the same for the distances now. I'm not going to try this because this does not result in a stable refinement. There is a way too much correlation between the parameters, but of course feel free to try that if you want to see how this turns out. So for the distances, we need to correlate the distances in a different way than the multiple scattering button. We do want to refine the distances because we know that the distances significantly decrease here when we refine the theoretical EXAFS function to the spectrum of the copper foil, and even more so when we refine it to the spectrum of the copper clusters. So what are the available options? Well, the available options are basically an expansion coefficient, which is the XYZ button here. This XYZ button basically uses only one parameter as a expansion coefficient, and then based on those parameters calculates the distances of all the single and multiple scattering paths in this refinement. This is one option. The other option is to refine not the distances itself, but a delta R. This is this button down here. If you click this, then all those are substituted by 0. 0 now means that the software uses the distances from the model structure and refines a delta R basically based on those distances from the model structure. This refinement using the delta R instead of R itself, the advantage is that we can now correlate those delta values to be all the same in this refinement. You can also use this to, for instance, correlate distances in a model structure that are very close together, but that needs to be taken into account in the refinement. Then you can correlate the delta R of those distances. And we will see an example for that in another tutorial when we look at metal oxides. Here, what we want to do is we basically want to have all those delta R values refined the same in the EXAFS refinement. So we just select the first one, select correlation, and now we want to correlate all those distances basically to the one parameter here that we selected. So this is the first shell, delta R, and all the delta R values of the other shells are to be the same in the refinement. So there are different combinations, different options now. Here there's an equal, as a plus minus a value. The sum of two parameters can be equal to a certain value or another parameter. So for instance, if you have two paths in a shell, let's say an octaeder, and you know that the coordination number is 6, then you can refine the coordination number of those two shells to be equal to 6. So 1, 2, or 1, 4, or both 3, or whatever. The pre-selected combination is basically times 1, so that means they will be the same. So if you do not change anything here and just transfer all those parameters, then all those parameters here, all those delta R values will be the same as the delta R value of the first shell. And this is what we want to have. This is basically a similar, this is the same color now, and it's a similar scheme that we're using for the E0 shift, where all the other E0 shifts of all the other single and multiple scattering paths are the same as the E0 shift of the first path. So now we are down to 12 parameters in the refinement, 29 independent parameters. So that should be sufficient. That should give a stable refinement. And so now we can give that a try. Click on OK, and the refinement is done. 22 iterations, and we obtain a reasonably good agreement between experiment and theory in amplitude, and of course also in the imaginary part. So I'm going to calculate confidence limits and the automated F tests now, because this is going to take a while. I will pause the video and then come back once this calculation is done. So the calculation is done, and we obtain the confidence limits and the F-test parameters. And we see significant correlation here between the Debye-Waller factors and the coordination numbers, which is to be expected, but we can see this here very clearly from the F-test and also from the confidence limits. Here, for instance, coordination number of 26 for this single scattering path with a confidence limit of 27. So, which basically means that this coordination number can be varied over a very wide range without too much influencing or changing the R value. So this is what the confidence limits means. Basically, the original R value here with a 95%. So you can vary this coordination numbers by plus minus 27 and still obtain a refinement with an R value which is within 95% of the original refinement. So very broad very broad confidence limits and strong correlation between coordination number and Debye-Waller factor. So although we are getting a good agreement between experiment and theory, this is not a viable refinement. This is not a reliable approach to determine coordination numbers and structural parameters in general from this type of refinement. So raises the question, what else is available? What are the alternatives? Here now, basically, we have refined 5 independent Debye-Waller factors together with 5 independent coordination numbers, and this results in those strong correlations. So that means we either need to decrease the number of coordination numbers that are running free in the refinement, or we need to decrease the number of Debye-Waller factors. So going back to the EXAFS refinement, going back to EXAFS refinement, we can keep all those shells and the range in the R space. We can keep the parameters. For now, we just need to input other constraints and correlations now in the refinement. So we are going to fix the amplitude reduction factor, and we are going to correlate all the delta R's to be the same. So now we have the coordination number and the Debye-Waller factors, and either one of those we need to decrease the number of free running parameters, and we're going to do this for the Debye-Waller factors because there's another option available here, and this is down here with a polynomial, which basically means that the Debye-Waller factors of the single scattering path will be calculated based on a polynomial, basically based on a line here with a polynomial degree 1. Well, this can be just reduced to 0, which is just one Debye-Waller factor then, or what we're going to use now is a polynomial degree 1. And so this leaves basically 2 parameters instead of 5. So we can click on correlate now, and what it does, it changes the color, and those 2 parameters here now are the coefficients of this first order polynomial, and this polynomial then is being used to calculate the Debye-Waller factors of the other single scattering and multiple scattering path. For the coordination number, we're going to use the multiple scattering button. So the coordination number of the single scattering path are free, and the coordination number of the multiple scattering paths are correlated to those. So this reduces the number of free running parameters by 3. Basically in the refinement. So now we have 9 compared to 29 independent parameters, and yeah, let's see how this goes in the refinement. So again, we get a reasonably good agreement between experiment and theory here now in the amplitude, and of course also in the imaginary part. And again, I'm going to calculate the confidence limits and F-test, and I'll be back once those calculations are done. So again, the calculation is done, and we obtain confidence limits and the F-test parameters. And again, we observe correlation, strong correlation between the Debye-Waller factor and the coordination numbers. We still have rather broad confidence limits here, although they are significantly decreased compared to the previous fit. So this is more reliable in terms of structural parameters, although we do want to be careful when interpreting those coordination numbers given the large confidence limits that we see here. But now we need to realize this is the best we can do. In the refinement, this is as far as we can go with reducing the parameters in the refinement while still maintaining some meaningful structural information now when we transfer this approach to the analysis of the copper clusters. Last thing we want to do now is we want to adjust the amplitude reduction factor, because we have a coordination number here now of 12.4, and we know in copper metal it's 12. So we want to adjust the amplitude reduction factor and then transfer this amplitude reduction factor to the analysis of the copper clusters. So just going to change this coordination number to 12, apply, and then adjust the amplitude reduction factor accordingly. So we need to increase this to about this value here, 9.4. Okay, so now we can close this and we're going to repeat the refinement. So we go to EXAFS refinement again. We can now keep all the flags because basically we only want to repeat the refinement with the change amplitude reduction factor, so we can keep all parameters now. So we do not need to change anything here. I'm going to set this to 9.4, make it easier. And with coordination number of 12 now, and now we can just start the refinement again and click on OK. No. Now we get a coordination number of 12.05 with this amplitude reduction factor, which is good enough now for me for the time being. And so now we can transfer this approach to the analysis of the copper cluster and see what results we get from this refinement then to the copper clusters and compare this to the results of the first shell analysis. So let's open the spectrum of the copper clusters, Fourier transformation, and now we can jump right at the EXAFS refinement. We're going to use the same approach that we just established for the copper foil. So use all those single and multiple scattering paths in the range, total of 21. Adjust the range and the radial distribution function. And now we're going to use the same correlations that we just used for the analysis of the copper foil spectrum. So we are going to use an amplitude reduction factor of 0.94. You use the multiple scattering correlation for the coordination number. All the delta R for all distances are to be refined the same. And we can just calculate the Debye-Waller factors using the correlated Debye model as starting parameters. And then we are going to use the first order polynomial and correlate that. So this is now being used in the refinement. So we are again at 9 free running parameters in the refinement, 30 independent parameters. So let's start the refinement. And again, we get a good agreement here in amplitude and also in the imaginary part. So I'm going to skip calculating confidence limits and automated f-tests now. They will basically result in very similar results that we already saw with the copper foil. So correlated coordination number and Debye-Waller factors, and still rather broad confidence limits. So if you want to see those numbers, then feel free to calculate that. I'm going to skip it here. And now we can look at the results of the single scattering path and compare those to the results of the copper foil and the first shell analysis. So this comparison is compiled here, where we see the results of the EXAFS refinement to the spectrum of the copper foil and the copper clusters, both including higher shells and only from the analysis of the first shell. So compared to the results of the copper foil, in both cases we do see a decrease in the coordination number, 11.1 here and 10.9. So good agreement here. We do see a decrease in distance in both cases, and we see an increase in the Debye-Waller factor going from the reference foil to the copper clusters in both cases when including higher shells and also only for the first shell analysis. So good agreement here between the two approaches, using only the first shell and also including the higher shells in the refinement. So raises the question, have we learned anything new now from including the higher shells in the refinement that we hadn't already known from the analysis of the first shell? Well, in this case, for copper metal and copper clusters, maybe not. But as I pointed out before, this is a copper metal sample. Those are only copper backscatterer in the first shell and also in higher shells. So this may actually change when you apply this approach to the analysis of more complex samples, structures, binary or ternary systems, where the analysis of the higher shells may actually indeed yield valuable results compared to the first shell analysis only. So, but this is enough with copper metal, and this is also all for this tutorial, and I sure hope to see you in the next one.